and gentlemen, welcome to lecture number 2. Today we will discuss the very important nut and bolt problem and displacement calculation for the tapered bar. These two questions are very important for your semester examinations and all the competitive examinations. First we will discuss the tapered bar problem, then we will go for the nut and bolt problem. Here is the first question. A steel plate 22 mm thick. So first we will write down all the given data. A steel plate 22 mm thick. Here the thickness T1 is equal to 22 mm and 220 mm wide. So B1 is equal to 220 mm at one end. Tapers uniformly to 12 mm. Means thickness T2 is equal to 12 mm and 180 mm wide. Wide width at section 2 is equal to 180 mm. This section is section 1 and this section is section 2. First we will discuss how to derive the result. Okay. Since we know for any bar, if there is a load P acting at the ends, then the deflection, this deflection delta, this delta is equal to PL by AE, where P is the load, L is the length of that bar, A is the area of cross section and E is the Young's modulus of elasticity. So this formula is applicable only when the area of cross section is constant throughout the length. But here area is not constant. Area is changing from B1 T1 to B2 T2. Right. So for that we have to derive the result. Let's take a section at L is equal to X. This is the section at L is equal to X. And we will find out the width at L is equal to X and the thickness at L is equal to X. So width at L is equal to X is represented as Bx. That will be equal to B1 minus B2 by L into X. Again the thickness T at X is equal to T1 minus T2 by L into X. Again we have to calculate the area at X is equal to Bx into Tx. Now we will calculate the deflection at dx length. This is the dx piece. This deflection for this element, dx element. So let's draw the element dx again. This was the element dx. Force is P. This is Bx and this is Tx. So here deflection, a small deflection for length dx is equal to del delta. That will be equal to PL by AE. Here load is P, length L is dx, area is AX and E is constant throughout the material. So E will be same E. Again we can write del delta is equal to P by AX. We have calculated. Here is the AX. We'll put that value in that equation. So it will be equal to B1 minus B2 by L into X into thickness T1 minus T2 by L into X. into dx. Now this dx varies from 0 to L, so we have to integrate it, and limit should be 0 to L. So delta is equal to integration of 0 to L. And question, we have load P is given here, this length is given 2.4 meter, and Young's modulus is also given 205 giganewton per meter square. This is equal to 205 into 10 to the power 3 Newton per mm square. This is equal to 20,000 Newton, and this will be equal to 2400 mm. We will put all three values into that equation. So it will be equal to 2400 by g1 is 220 minus 220 minus 180 by length is 2400 into x. t1 is equal to 22 minus t1 minus t2 is equal to 10 by 2400 into x into dx. This L is 2400, but load is 20 kN. If we solve that integration, then we will get the required displacement delta. In calculator we have a function of integration, so we will just use calculator. Here I have solved for you. I have put all the load value P, value of E, and all Bx and Ax and Dx. We are getting 0.0719 mm. So delta is equal to 0.0719 millimeter. This will be the answer. In this nut and bolt problem, the pitch is given as 1.6 mm and copper tube is free from any stresses. There is no stress on copper spacing tube, and we are asked to calculate the stresses in the tube and in the bolt if the nut is turned by an angle 90 degree. Here Young's modulus is given for copper EC and for steel ES. This one and this one. First we will understand what is pitch. You might have seen a bolt. Let's say this is a bolt. In bolt there is always one thread like this. And if a nut is tightened by 360 degree, then that nut moves by a small amount. That is known as the pitch, this distance, and we represent that pitch as delta. Now first we will understand the problem. I am drawing that problem in 3D view so that you can understand easily. We have a copper tube. This is a copper tube, and inside that copper tube we have a steel rod like this. This rod is nothing but our bolt, right? If we tighten the nut, this one, this is the nut, then that nut will move by some amount. That will be known as the pitch. And if you tighten the nut, then that bolt will be in tension and the tube will be in compression. Now we will draw the pre-body diagram of that copper tube and the bolt. Let's take two sections. This is the one section, this is the other section of the copper tube. Since the copper tube is in compression, everywhere there is a compressive stress. Our bolt is in tension, so on bolt we have a tensile stress sigma S working, and on copper we have sigma C compressive stress. This problem can be solved by using only two conditions. One is the equilibrium of the element and other is compatibility condition. We'll see one by one. First we'll see the equilibrium condition. Total force acting on the copper tube will be equal to stress on the copper tube, that is sigma C, and area of copper tube, AC. And total force acting on the bolt will be equal to sigma S and the area of the bolt, AS. This area is AC and area of bolt is AS. So, for equilibrium of that element, the total force on the copper tube should be equal to the total force on the steel tube. That is sigma C into AC is equal to sigma S into S. Here we will get sigma C is equal to sigma S into AS by AC. This is our first lesson. We'll write the first lesson, equilibrium relation. Sigma C is equal to sigma S into AS by AC. Now we'll move to compatibility condition. Compatibility condition. We have discussed that bolt will be elongated and there is a compression in the copper tube. So, elongation in bolt is equal to compression plus compression in tube, that will equal to the amount by which the nut is turned. Let's say it is equal to delta L. Now we know the formula for elongation. It is equal to PL by AE. We know delta is equal to PL by AE. Here P by A is known as the stress sigma, so delta may also be written in terms of sigma like this. Delta is equal to sigma L by E. So here we can write elongation in bolt is equal to sigma S LS by E, but length of bolt is equal to the length of tube, so we will write it as L plus compression in tube, it will be equal to sigma C into L by E of tube, that is EC, E of steel, that is ES. Both will be equal to by amount by which the nut is turned, that is delta L. Note that this delta L is not pitch. This is the amount by which the nut is turned. We'll put value of sigma C from equation 1 here. We'll take sigma S as common and we'll get L by ES into AS by AC into L by EC is equal to delta L. Further, if we resolve to calculate sigma S, we will get sigma S is equal to delta L by L into 1 by ES plus AS by AC into 1 by EC. This is equal to required stress in the bolt. We have to also calculate the stress in the copper tube, that will be equal to sigma S into AS by AC. Now we'll move to the problem, and using these two relations, we will solve the problem. Here, area of copper tube is given. AC will be equal to 5 by 4 into 18 square minus 12 square. It will be equal to 141.37 mm square. AS is equal to pi by 4 into dia is given as 10 mm. It will be equal to 78.54 mm square. Now we'll calculate the amount by which the nut is being turned. If we turn the nut by 360 degree, then it will displace by amount of pitch, that will equal to 1.6. But here the nut is being turned by angle 90 degree. So if you turn the angle by 90 degree, the amount by which the nut will move will be equal to 1.6 by 360 into 90 is equal to 0.4. This is the delta L here. The value of ES is given and value of EC is given. ES and EC. ES. We have written everything in a systematic manner. We have calculated AC, AS, then the ratio can easily be calculated. AS by AC it is equal to 0.556. The amount by which the nut is being turned, we have calculated this, 0.4 mm. AS and AC are given. We have converted from GPa to Newton per mm square. We have already derived that two formula. We will put all the values in this formula and we will get the result. For calculation of sigma s, we will use calculator to calculate, and if you put all the value, we are getting 386.67 MPa. So 386.67 MPa is the answer for sigma s. Sigma c can be calculated by putting sigma s here. It will be equal to 386.67 into 0.556 to 14.98 MPa. Here we come at the end of second lecture. The next question will be discussed in the next video. I thank all of you for your patience and SemExcel team for writing all the questions on the slides. Thank you very much.